Thank you to Emily for that wonderful introduction to our symposium. I'm going to quickly introduce Dr. David Stork, who is a Rambus Fellow at Rambus Labs and leads research into its computational sensing and imaging group. He's a graduate in physics from MIT and the University of Maryland and studied art history at Wellesley College. For nearly 20 years, he and his colleagues have pioneered the application of rigorous computer image analysis to problems in the history and interpretation of fine art. He has taught courses on this subject in both the computer science and art history departments at Stanford and published over 45 technical papers. He's lectured in 20 countries at major museums. He's a fellow of the International Association of Pattern Recognition, of the International Academic Research and Industry Association, of SPIE and IEEE, and of the Optical Society of America. He's published over 200 technical articles, 8 books, including the leading textbook on optics in the art and pattern classification, the world's all-time best-selling textbook in the field. Please welcome David Stork.
Thank you very much. I'd like to show you what several of my colleagues and I have been pioneering starting 20 years ago on applying computer vision to problems in the history and interpretation of fine art, including these paintings and many others. And I'd like to start with Vermeer's masterpiece, Girl with a Pearl Earring, and Vermeer, of course, was a master in rendering the effects of light. Look at the glint off her eyes and her lips and the shadows and so forth. But if we were to ask the simplest technical question about this illumination, it would be, what is the direction of illumination? And if two art historians disagreed, how would we adjudicate? How would we tell who's right? Well, let me show you 6 methods from computer vision that solve this problem absolutely clearly, and then tell you how it changes our understanding of this painting and it can be used elsewhere in the history of art. The methods fall into 2 categories. The first are model-independent methods, where we don't need to make any assumptions about the 3D form in the Tableau. We'll look at the shadow cast by our nose and what's called the Occluding Contour algorithm. And then model-dependent methods, where we do need to make some assumptions about the 3-dimensional form in the Tableau. We'll look at the 3D model of the pearl, of the eye, of her face, and the entire Tableau. So the simplest method is cast shadow analysis. You take a point on an occluder, its corresponding cast shadow point, draw a straight line with error bars, and you find for this painting the light is coming from a direction of 150 plus or minus 2 degrees, where throughout I'm going to measure directions with respect to the horizontal like that. The occluding contour theory or algorithm comes from a branch of computer vision called shape from shading. It tells you how to interpret the 3-dimensional form of an object and the brightness of it depending upon the normal, sort of an arrow off the surface, the unknown direction of the illumination, and so forth. And I won't go through the math, but if you knew what the normal was, if you knew what the shape of the face was, you'd be able to, the computer algorithms can then go through and say what direction of illumination is best consistent with the entire face. Unfortunately, we don't have a model of her face for this. 2 computer vision experts, Nelius and Eklund, came up with a very clever solution to this. They said, all right, we don't know what the normal is through her face in the middle, but we do know what it is along the outer boundary or occluding contour. The normal is perpendicular to this contour, and it's in the plane of the painting, not towards us, not away. It's like a flagpole on the horizon. And that makes the mathematics simpler. I won't go through it. But it allows us to then set up a system of equations that allow us to then infer from the pattern of light around the outside contour the direction of illumination. Well, it turns out this method was, so here's one way to think about it. Here's an object, and if we have a dark patch here, that alone would not allow you to tell what the direction of illumination is. But if I measured the brightness along the entire contour, look at this patch. It's bright. It's probably facing towards the light. This patch is dark. It's probably facing away from it. And the mathematics I just went through takes all these measurements and says what direction best explains this entire pattern of lightness over the contour. Well, this technique was actually invented not for paintings, but for forensic photography. There was a photograph of Brad and Angelina that sold for $500,000, And not to be outdone, the Star published this painting, this photograph. You can see where my head is. This photograph, and using the occluding contour algorithm I just showed you, Hani Farid showed that the light on Brad was coming from this direction, and on Angelina it was coming from this direction. This was photoshopped. And it was exactly this technique that showed it. But this also shows how bad humans are at detecting light. That's why there are so many fakes that get by us. But these computer techniques find them absolutely perfectly. And so when you apply that, we were the first to ever apply it to a painting. So you apply it to the Vermeer, taking this contour here. It says, this is the direction to the illumination, 149 plus or minus 4 degrees. Now for the model dependent methods. I took a high-resolution photograph of the pearl in that painting, and we can confidently assume that it's cylindrically symmetric. And so I built a 3D computer graphics model, and you now so-called texture map it, put the white on it. And a pearl has a specular or mirror-like reflection, so you have to adjust by eye the relative components of the diffuse reflection and the highlight reflection. And now in our computer model, we can put the light wherever we want in order to render the pearl, the digital pearl, so that it matches that in the painting as closely as possible. And then we have an estimate to the direction of the illumination. And that turns out to be 155 plus or minus 4 degrees. What about the glints on her eye? If her eyes were spheres, then the position of the glint on her eye is related to the unknown direction to the light by a very simple formula. It's really just the law of reflection. The angle of incidence equals the angle of reflection. But of course, an eye is not a sphere. It has a corneal bump that pushes out. And so we have to find which way that bump is pointing. We fit an oval to the iris or colored part of the eye. And in this painting, she's looking, they turned out to be perfect circles. She's looking directly at us, or really directly at Vermeer. And you can see the center of mass of the reflection. So in the computer model, we know the direction of the eye, and we have a model of it. It's high school physics, optics, in order to then calculate that the direction to the illumination is 150 plus or minus 2 degrees. The most sophisticated technique we used comes again from this notion of shape from shading, this algorithm of shape from shading. If we had a model of her face, we could then say, the computer could answer, what direction of illumination on this model would lead to the pattern of lightness that we find in the painting? The problem is we don't have a model of her face. So we did the next best thing. We used a generic model, it's actually a man's face, and adjusted the pose to match her face as closely as possible. And we temporarily assumed that was her face. And then the computer gets an estimate that says, for this model, for this face, this direction to the illumination will best explain the pattern of lightness we get in the face. But of course, it's not going to be right because this isn't the proper face. So then we assume that the light is correct, and we fix the face, or the computer fixes the face to get a better model of her face. And now we have a better model of her face, and then we can re-estimate the direction to the illumination. The computer scientists in here will recognize this as the EM, or expectation maximization algorithm. And at the end of the day, you have a better model of her face and an estimate to the direction of the illumination. Turns out to be 160 plus or minus 5 degrees. The most the funnest part was making a computer graphics model of her face, of the entire Tableau, and now we can turn it around. Now, this is technically, when I showed this at the Maritz house, the friends of the Maritz house went crazy because they'd never seen the back of their painting. You have to make an assumption. This is technically called an Illposed Problem. You have a 2D image, and you have to make a 3D model. You can do this. There are a number of techniques from computer science. All you need to know is that it doesn't add a bias to the estimate of the direction illuminated. It doesn't mean the light's going to be too high or too low. There's going to be uncertainty, but it doesn't bias it, and we can incorporate that into the models. So now we ended it in the pose, and we can move the light around wherever we want, and then we're going to stop that portion of the film where in the configuration that best matches the painting, and now we're going to fly around Vermeer's studio and look at her from all many possible directions, and then I'm going to stop it in the configuration that matches the painting and do what computer graphics people call an alpha blend, basically a blurring from the computer model to the actual painting, and you'll see that it matches extremely well. And that now gives us yet another estimate to the direction of illumination. So here we go. And so here are three stills from that movie, if you will. One where the light's too high, and one where the light's too low, and so forth. But here are results from all those techniques. Here are the angles, and the average turns out to be about 155 degrees. That's actually not very important. What is important is the very small standard deviation, the incredible agreement among these 6 different techniques that are very, very different, like the Pearl and the Occluding Contour algorithm. One way of looking at that is, showing this is, the red line is in that 155 degrees. That's the direction to the illumination. And the yellow line is called a cardioid. It tells us, in this case, the relative probability of finding the light in a given direction. So it's most likely the light's in this direction. It's about, I don't know, half as likely off in this direction. The fact that the yellow cardioid is so long and stretched out shows the incredible agreement among these different methods for estimating the direction to the illumination. Okay, so what? Why would an art historian be interested in this? Well, this is not a portrait. We don't know who this person was. It's called a trony. It's sort of a character sketch. And some art historians actually debated whether there was a person present during this. Maybe he just did it out of his imagination. Well, the fact that these methods agree so well almost certainly shows that there was someone there present so that he could observe the position of the glints and so forth. And this technique can be used elsewhere, especially in Renaissance art, when you have maybe 4 or 5 different figures. Maybe they are done by one master and several assistants in the atelier, and if the lighting is very different on them, they might have been done at different times, different studios, and so forth. That's evidence to tell whether they're by the same hand or at least the same studio. And so this can be used elsewhere. Now I want to use one of the examples from art history that sort of got me into this debate, or into this field, and it came from the artist David Hockney. Maybe some of you remember that he looked at this transition. When you stand back and look at the grand sweep of the development of Western painting, you find there's this transition around 1430. Before that time, images were somewhat awkward and schematic. If you look at this Giotto fresco portrait, you look at the ear, it looks like a cartoon. So this anonymous Austrian portrait of a king, and this lovely Masolino, almost porcelain doll-like portrait. But after this time, you get paintings like this. Robert Campin's A Man of 1430 in the National Gallery in London. It looks so realistic, almost photographic. This portrait has a personality, an individuality, a psychological depth lacking in these earlier works. This guy looks like us. What happened? Well, in order to explain the emergence of this new art, David Hockney came up with a bold and very controversial theory. He believed that these later paintings were optical, as he called them, because they are optical, that Renaissance painters secretly used optical devices during the execution of their works. And here's Hockney showing how he believes it was done. Here he is in Santa Monica, California, my home state. Very important, a lot of sunlight. The subject is outside, there's a window here, and the key element in all this is a concave mirror, which anyone in physics can tell you can project an image just as does a lens. The image is on the other side of the wall there. It's upside down, it's so-called inverted. The artist would trace it, and then bring it down, and then turn it around and paint over it while he's tracing. Then he would then paint over it with oil paints or acrylics later or whatever like that. And so that's his theory of how this realism came around 1430. Well, one of the paintings he adduces as evidence is Georges de Latour's Christ in the Carpenter's Studio in the Louvre, incredible masterpiece. And he says that in France, the most famous of Caravaggio's followers was Georges de Latour. Could that candle really produce all that light? Once again, the source of light seems to be outside the picture, as it must be if you use optics. If the source of light were in the setting, it would cause flare in the lens. Joseph and the girl, it's not a girl, it's Christ, were probably painted separately, each lit by a shielded light source in place of the other figure. So in his book, Secret Knowledge, he shows this. He says, when Christ was being painted, the light source was in place of St. Joseph. And when St. Joseph was being painted, the light source was in place of Christ. or outside the picture frame. So you have to look at this and try and figure out where was the light source in this. And humans aren't that good. Computers are superb. So we approached that and said, all right, first thing to do is cast shadow analysis. You take, for instance, a shadow cast by the left thumb of St. Joseph, draw a line from its, the occluder, from the shadow point right through it, bingo, goes straight to the candle. The candle flame is behind Christ's hand. This is smoke, if you know this painting. And then if you do a full set of such cast shadows, indeed, there is one with a very small sort of moment arm that's consistent with the light being in place of Christ. But the vast majority, including the cast shadow from St. Joseph's nose, all meet right at the candle. And you can see these contours. These are contours of equal a posteriori probability density. It's just a lot of words. It just says the light's most likely here, less likely here, less likely here, less likely here, like a high weather, like a high pressure region on a weather map. And I won't go through the mathematics, except graphically to say, if one cast shadow says, the light's in this direction, would this fall off? And the other says, it's in this direction. Basically, you multiply these together. Think of these as sprinklers shooting water each, and where is it going to be the wettest? That's the most likely place for given all this evidence. And that's all I showed on that previous slide. But then we could also use the occluding contour algorithm, and you can have contours along the arms and the hands and the wrist and so forth. And so the computer puts in all of these red lines. The computer doesn't know anything about Baroque art. It doesn't know about Christ. It doesn't even know 3 dimensions, really. It just has a contour and then measures the light along that contour and then infers the direction that the light's coming from. Look at Christ's shin. This is unbelievable to me, that the computer just gets this curve and the pattern of light and it says, the light's right along that direction. Bingo, right to the candle. Everyone has admired the lighting, the ability of de la Tour to render light, but I don't think people really appreciated how amazingly well he was to render the shin so perfectly that the computer knows that the light must have come in this direction. And then you can do the same probability estimate for all of this evidence, and again, the light, it's most likely the light for this evidence is right here, less likely here, and so forth, right at the candle. We've done it on other paintings here in LACMA, and one of the benefits of using this probabilistic approach, this machine learning approach, is that you can now integrate the evidence from disparate methods. So here's the evidence I showed you for the cast shadows. Here's the evidence for the occluding contour algorithm. And to put them together, you basically just multiply them. And so putting both of those together, it says, it's most likely the light's right here, less likely here, less likely here. Certainly not outside the frame of the painting, as Hockney believes and is necessary for his theory. But there's other lighting evidence in this painting that we have not yet used. Look at the pattern of light over the floor. It's bright in the center and dark off to the side. Where would a light source be so as to make the center bright and the sides dark? Well, it's not going to be over here. It's not going to be over here. It's going to be somewhere in the center, and we make a physics model of it. It's high school physics. I don't expect art historians to do it, but I do expect any computer scientist to be able to do this kind of stuff. And what we want to do is find the position of the candle or of a light source and other parameters like the tip of the floor that best explain the pattern of light that we find on the floor. And this is all the math. And then so this is the change of on the floor of changing the height of the candle. Here is the tip angle of the floor, and so forth. So the computer is trying to search around. What's the tip of the floor? Where's that candle in order to explain the pattern of light that we find in the painting? And when you go through and do that, you find that the position is here. Now, it's somewhat low from the actual candle, and we think we understand that. A grad student at Stanford and I figured this out, that it's that the range of lightnesses you get in the real world might be a factor of 100,000, maybe a million to 1. paint only has an albedo ratio. The whitest white to the blackest black is only about a factor of 100, and that shifts the position. Nevertheless, it's consistent with the light being in the middle, not outside the frame of the picture, as Hockney says. So he's just simply wrong on this one. But there's yet more lighting information that we have not yet used. All the pattern of light over Christ's chest, over the entire objects that are not along the outer boundary and are not casting a shadow, just as we had for the girl with the pearl earring. So we have to make a computer graphics model, and this can be done semi-automatically, and there are increasingly ways to do this completely automatically with certain assumptions. And now we're going to, so here's the digital tableau, and we're going to put a light in place of St. Joseph, and then one in place of the candle, illuminate the Christ model, and then decide which one best explains the pattern that we find in the actual painting. The problem is we don't know the depth into the tableau. Was the light here, 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 here in the model? So we did 19 and chose the best one for the light in place of St. Joseph, the best one for the light in place of the candle, and rendered Christ. But before I get to the results, here's the full computer graphics model. Now, if you study art history, St. Joseph's the carpenter, so he has the tools. Christ is the light of the world. He has a candle. So I hope you can see that the cast shadow is changing here on the floor as we adjust the position of the illuminant inside the tableau. And now I'm going to stop it and look at the back of the painting. We're going to look at the tableau from all the way around, and then stop it in the configuration that matches the actual painting, and do another alpha blend to see how well it matches. And here are our results. So here's the actual painting. Here's the best image you can get with the light in place of St. Joseph. Here's the best one you can get with the light in place of the candle. And you say, which one actually matches the actual painting best? And there's no question, none whatsoever, that the light in place of the candle matches the actual painting much, much better. Look at the pattern of light over Christ's chest. Look at the cast shadow of the shin and knee. They're not exactly the same, but it's much, much better here, and so forth. No question that the light was in place of the candle, and Hockney was wrong. Another painting that came up in the debate is this Van Eyck's incredible masterpiece in the National Gallery in London, the Arnolfini portrait. And in art history, you'll learn immense amounts about the symbolism and the importance of this painting, but we're going to look at Hockney's claim that this was done using some sort of projector. Well, if it was done some sort of optical system, we can infer what focal length would have been used. Here's an example of how you do it with photography. This is a photograph of me many years ago as a beginning assistant professor at Swarthmore, taken with a wide-angle lens, 24 millimeter short focal length lens. Notice the size of me and the size of the pillars here. Then the photographer put on a normal lens, 50 millimeter, magnifies everything by a factor 2, but he moved back from me twice as far so as to ensure that I'm the same size in these two photographs. But look at the pillars. Pillars appear larger. Then he put on a telephoto lens and moved back the appropriate distance to make me the same size. But now look at the pillars. These are all in perfect perspective. They're photographs, after all, but it's just where the center of where the camera is, the center of projection. Well, if you have such a photograph or a tracing of a projection, and you know the relative sizes of the objects, you can work backwards and infer what focal length was used. Really, everyone in this room can do it. I teach my undergraduate art history majors at Stanford how to do it. Everyone can do this. But you need to know or make some assumptions about the 3D form in the tableau. So we made a computer graphics model of the Arnolfini tableau, and here it is from the side. And here is the painting to scale in this digital realm. And then you ask, where would I put a lens? It turns out to be the same as with a lens and a mirror. I won't go through the optics too closely, but where would I put a lens such that the sizes of the projected images match that of the real objects? Of course, they're not real, it's all digital. But if you put the lens here, then the size of the image of the chandelier corresponds to the size of the real chandelier. The size of Arnolfini matches Arnolfini, in fact, 13 objects and image pairs. And once you have the lens here, not here, not here, but here, you have what's called the image distance, the object distance. It's high school optics to calculate the focal length of this lens. Turns out to be about 61 plus or minus 8 centimeters. Well, Hockney and his colleague Falco wrote that Van Eyck placed a convex mirror at the very center of this Arnolfini masterpiece, the very mirror which, turned around, he may well have used to construct this image. And you're all familiar, everyone in this audience is familiar with this incredibly detailed reflection off the curved mirror at the center of the Arnolfini masterpiece. You see the back of Arnolfini, you see the back of his wife, you see the two witnesses to the wedding coming through, and it's clearly distorted. You can see the bending of the lines in the rectangular mirror and the bed and so forth. And so we published 4 papers on methods to de-warp this image and thereby estimate its curvature, which then tells us its focal length. And one of them involved, well, here's a picture of one of my Japanese colleagues taking a photograph of a curved mirror, a security mirror at the top of his lab, and you notice that lines that we know are straight, the hallway lines, are in fact distorted and warped. And so mathematically we can undo that, and in doing so we get a measure of the curvature of the curved mirror at the top. And so when you do that, you can unwarp the image or dewarp the image, get every line that's supposed to be straight appear indeed straight, and then we get the focal length of the mirror, and we can undo that distortion. And so here's the undistorted view in that little piece of the Arnolfini portrait. This is an amazing image. This is the view you would get if you were to walk into Arnolfini's room, stand at that mirror, turn around, and look back, revealed nearly 500 years after this painting was made. And you notice that the window is much more rectangular, and the perspective is much, much better, and so forth, as we've quantified. But this gives us the curvature of the mirror, and that means the focal length. Well, and so here's the mirror on the back, and if Hockney and Falco are right, the focal length of this should be pretty close to the focal length of the putative projection mirror or lens. But when you go through the math, it turns out the focal length is 18, plus or minus 4 centimeters. Much, much, much too short. It simply could not have been used as claimed. There are a number of other reasons. It would have been distorted, so you wouldn't have gotten a good image. They coated the backside with tar so as to keep the metal from tarnishing and so forth. There are plenty of reasons why they're just simply wrong on that. So here from my Scientific American article is a way to visualize this. So here, the putative projection mirror, and its focal length is 1/2 the diameter of this sphere as represented here. Here's the sphere that would be for the mirror on the back. Much, much, much too short to have been used as they claim. Well, okay, well, maybe this mirror wasn't used, but what about other mirrors? Could another mirror or lens have been used? No. Why? If you do a perspective analysis, you find that, for instance, on the floor, these two perspective lines meet here. This one doesn't meet it at all. These are parallel lines. They never meet at all. That the perspective is just not coherent. It doesn't, which you would get if it were done under a single projection. This does not mean it's a bad painting. Some art historians say, oh, Stork thinks that if something's not in proper perspective, it's a bad. Not saying this at all. This is a sophisticated art. I don't have to explain that. But, okay, so not for that, but what about that chandelier? David Hockney got on CBS 60 Minutes and told 8 million people, quote, that chandelier is in perfect perspective. And then he goes on to build a projector and say, I would have traced it this way and so forth. I thought I'd check. Here is the 6-arm chandelier, a plan of the bird's eye view. Looking down here, the arms of the chandelier, 1, 2, 3, 4, 5, 6. Consider 2 points on corresponding arms like those decorative crockets that hang down beneath. Those define a line in Arnolfini's room. Think of my 2 arms as chandelier arms. This elbow and this elbow define a line in this room. That line is parallel to the floor because my elbows are at the same height. That line is also perpendicular to the vertical plane bisecting these 2 arms, okay? Think of other crockets. Those also define a line, like my 2 thumbs. Those define a line. That's parallel to the floor because these are at the same elevation, and perpendicular to this plane. So those two lines are parallel in Arnolfini's room. Likewise, here, all of these. So here's what I've just shown you, those lines. If you think about symmetry, it's same for the lines defined by these two arms. They're all parallel. And if you really think about it, lines defined by corresponding points on arms 2 and 5 are also parallel. All of these are parallel lines in Arnolfini's room. So we built a symmetric computer graphics model of the chandelier. And if it's in proper perspective, of course it is, it's computer graphics, then if we take the images of these lines, for instance, a line from this crocket to this crocket, extend it. This crocket to this crocket, extend it. And all of them, they better meet at a vanishing point down here. And when you do it, well, sure enough, it's computer graphics, of course it's going to work. What about the Arnolfini chandelier? If it's in proper perspective, we should do the exact same construction, draw a line from here to here, extend it, here to here, extend it, and we should get a vanishing point somewhere down here. But when you do it, here's what you get. Kaboom, it's a mess. An absolute mess, not even close to being proper perspective, not even close. Even famous artists and art historians are really bad at being able to tell whether something's in proper perspective, but the computer techniques can find it really, really simply. And here's another way of looking at it. So here's one of those lines, extend it. Here's another line, extend it. And here 15 just from the left-hand side. Not close to having a vanishing point. Down here, not even close. So how far off? When I published this, they came back and said, well, maybe the chandelier was really poorly made. And so I calculated how bad would the chandelier have to be consistent with their theory. Well, you take a point down here, it goes through this point, and it should go through these, and what you find are a whopping 8 to 10 centimeter variation. Well, is that what you would have gotten? Absolutely not. Antonio, my colleague from Microsoft Research, and I did photogrammetric analyses of denandry, the decorative metalwork, this time in the Renaissance, and found that they were all highly, highly symmetric. Then we spoke to experts in denandry who said that, oh no, these arms would all have been made from the same mold. You'd make 6 identical arms and then array them around the post. So you would not, and I even went up the street to the Met and measured one of their chandeliers of the same time, symmetric to about 1 millimeter, not 10 centimeters. So that explanation simply cannot hold. Another way of looking at this is doing what computer scientists call a homography, mapping a plane with one arm to a plane with the other arm so that you can compare the arms completely. If they are perfectly the same shape, it's simple mathematics. But when they have different shapes, you can always make a homography where the thumbs will overlap, but then the elbows don't. Or you can make another one where the elbows overlap, but then the thumbs don't. You want to get the best overall mapping, and my colleague Antonio Cremonese did the mathematics on this and figured it out how to do it. I won't go through the math, but it's basically the best mapping, there's the math, from one arm onto another. And so there are 2 arms being shown here, and again, you get this whopping 8 to 10 centimeter disagreement between the arms. Much, much, much too large to be consistent with Hockney's theory. Well, one of his motivations was that, oh, no artist could have really drawn that chandelier in such good perspective entirely by eye. He must have used some sort of optical device. Is that true? Well, I had a realist artist paint 2 chandeliers entirely by eye so that I can analyze those. But first, here's the Arnolfini chandelier, of course, and it turns out one small portion of the chandelier is in good perspective, the bobesh or the candle holders. If you take a hexagon, you can do the homography and find that it matches pretty well, a little bit off, but pretty well. Well, here's this chandelier with 5 arms. You do a pentagon by Nicholas Williams, who lives in southern England, and it turns out it's in slightly better perspective than Van Eyck. In fact, the whole thing is in better perspective. And then he painted this really beautiful chandelier, 2, entirely by eye, no projections, no rulers, nothing, just by eye. And it's in superb perspective, as I'll show you on the next slide. Superb, except except you can't see it, but the computer finds it immediately that one of those arms is a little bit off, statistically significantly off. And when I found this out, I emailed him, what's going on? And he said, oh yeah, I accidentally dropped the chandelier, and one of the arms bent off at the bottom. And I calculated 1.5 centimeters, 1.3, close enough. So now let me show you just how good the perspective is on this eyeballed chandelier. We take one of the arms and segment the background. So here's one of the arms, and here's another arm. We just erase the background, so to speak, and then do the mathematics I just whipped through and take one of those arms and overlap it to the other. So that takes arm one and transforms it to be as similar to this as the other. Now, the homography maps a plane to a plane, so things that stick out of the plane, like the pan of the candle holder, won't match. So don't worry about this, just look at the shape. And when you overlap them, they overlap superbly, incredibly well. He did this entirely by eye, and he admits fully that he's not as great as Van Eyck, so you don't need any sort of optical help in order to draw the Arnolfini chandelier. Well, now I could talk for weeks on this kind of stuff, but I now just want to present you my vision for where this field should be going. Here's a painting. I've actually published 3 or 4 papers on the carpet on this. I don't have time to talk about that. But imagine the following. Imagine we had all the art historical knowledge that we have properly organized using computer techniques and so forth, and then we found this, but not anything about this painting. It's not in our database in any way, shape, or form. And someone found this painting. We would want our computer to do the following kinds of things. We would want it to tell us that it's an oil painting, not an etching or watercolor or something like this. That it's a double portrait, that there's a man there and there's a woman there. Judging from their clothes and the jewelry, they're fairly wealthy. That in the back, it would have to figure out, it's easy for us to see it's a window, but is that a painting on the back wall? But we want our computer to figure out that it's a window and that there's a storm outside, and that means that they are safe from the storm. They are together reinforcing each other and loving each other and so forth. And of course, there's a dog here, and at this time, of course, everything's period contextual. At that time, it means Fidelity. It means she's always going to remain faithful to him. It's very difficult to see, but there's a squirrel down here. And the man's pointing to it and holding homo nunquam, man never. Well, the squirrel signifies skittish wandering or lusting after other women. And so he's pointing to it and said, I will always remain faithful, homo nunquam. But very unusual for art of this time, her head is higher than his. You almost never get this in the Renaissance. Well, records show that this painting was painted several years after this woman died. She's in heaven. And notice the style of her face. It's much more ethereal and smooth and so forth, whereas the man's much more earthy and ruddy and in the here and now. And if you really look closely, you can tell that his eyes are red and that he's been crying. So this is a painting sort of documenting that he's going to remain faithful to his wife even after she's dead. Now, somewhere in that Art 101 mini lecture, there are things that computers can do right now, no problem. And then there's the stuff at the very end that is very, very difficult and will take us a long time. But there's nothing in principle against getting a machine to do what I just went through. Not going to a database and finding what some art scholar has published on this. That's a very simple problem, indexing and finding background information, but actually doing the evaluation that an art historian would do. It's years away, but I think with the kinds of techniques that I and my colleagues here and elsewhere around the world are working on, it's a doable process. And I think we are now in an era that's like what Morelli was, who really brought the sort of scientific notion of connoisseurship to art history, identifying painters by how they rendered hands and ears and so forth. Let's not forget, Morelli was a medical doctor. And so it was his power of observation and coming from outside art history and saying, here's some techniques that have helped me understand to diagnose diseases. Maybe these can be used in art history. so too those of us working in computer vision have lots of techniques that we'd love to work with art historians for revolutionizing how we study art. Thank you very much.